Pens up. Let's draw a diagram. Okay. A smooth circular cone. Okay, I'm going to draw it like this. Okay. You don't know where it ends. They don't tell you how tall it is. It doesn't matter though, because it's all pretty consistent. There's my cone. Vertex up. Axis is vertical. Okay, so there you go, facing upwards, is not at an angle. It has a semi-vertical angle of 60 degrees. We know what semi means, right? Semi, think about like conics. Semi just means half, right? Like semicircle, okay? So the semi-vertical angle of 60 degrees is in there, okay? A particle of mass 1 kilogram, mass 1 kilogram, is attached by a light inelastic string from a point vertically above the vertex of the cone. So I'll call that C up there. P moves with constant speed, v meters per second. So that's a linear speed, isn't it? It's not an angular speed because it's meters per second, not radians per second. V meters per second. On the outer surface of the cone in a horizontal circle. Okay, so it's sitting on top of this cone, and it traces out this circular path here. Okay, so let me draw that in. That's pretty awful, but you get the picture, right? So there's P over there. Okay, it's moving around, and that horizontal circle has a radius of 0.5 meters. So here is the center of the horizontal circle. I guess we'll call that O. Okay? And that radius there, 0.5 meters. Okay? The string makes an angle of 30 degrees with the vertical. So we already worked out where the vertical is. It lines up with the axis of the cone, 30 degrees. Okay, so then there are a few questions. And I'll leave this guide here, okay? Part A, can we get a horizontal force and a vertical force? There's the first question. Second question, if we know what the velocity is, let's call it 1 meter per second, okay? Find the magnitude of the tension in the string and the reaction force on the cone, on P. I'll talk about that in a second. Of the cone on P. Okay. Last question. I'll read it to you. Find the maximum value of V. Find how fast you can go. That lets P maintain contact with the cone. Find the maximum value V that lets P maintain contact with the cone. Okay, you now know this, right? We looked at this, we just derived this example, okay? If I increase V enough, right? Right now it's on the surface of my imaginary cone there, but if I increase V, it'll lift off. Okay, does that make sense? So there's clearly some upper limit on what that velocity is. We want to try and find that, okay? So, maximum V to remain on cone. Question mark. Okay, have a go. Start off. Remember, we've already started our diagram, but there are no forces on it yet. Okay, so why don't you put all the forces there? Use colors if you can, because it really helps you distinguish all of them. And then I'll give you a couple of minutes head start, and then I'll do it. Okay? Okay. So the first easy bit is your gravity, no problems. Okay, it's mg, but you know that the mass is just 1. So I put the 1 there just kind of for completeness' sake. Okay. So there's gravity going down. Then you've got tension going up along the string. So far, so good. So you've got a vertical component, you've got a horizontal component. Has anyone worked out what those are yet? Anyone worked out what those are? Okay, have a look. Let's just do it quickly now. Okay, you've got this angle in here, right? So you can work out what this is through the same trig sort of thing that we worked out before. Okay, I'm pretty sure it's going to be, you have 30 degrees here, right? So you want this, and it's the adjacent side, so it's going to be t cos 30. Is that okay? I know you know what cos 30 is, but I'm just showing you that so you can see where I got it from. Same deal, you're going to get t sine 30 going in the horizontal direction. So I'll just squeeze that in. Okay, now, I've accounted for 2 forces, right? And I've resolved them up, down, left, right, okay? But there's a force I'm missing. Okay? Now, it's easy to illustrate if I show you something like this, okay? So, you've got an object and it's resting on a surface, Okay. Now, at least at the moment, it's not going anywhere, right? So you've got gravity going down, and then you've got reaction force going up, and that's why it stays put. Okay. But now, if I tilt this, right? So I'll move this up here. If I put this at an angle like this, well, it slides off. Wait, what happened? Why did it slide off? I wasn't pushing it or anything. What was exerting force in another direction to make it move? Because we know, because of inertia, if there wasn't some force making it move, it would stay put. Why, when I tilted it, did it go, floppy board. Did it go from its stable position to its unstable position? Why? Why? This is all I did, I just tilted it like that. Okay. And the answer is, right, the reaction force that's being exerted by this book, it will exert only in one particular direction, namely, whatever direction the surface is facing in. Now, right now, that surface is exactly opposite facing to gravity, directly up. But the second it's not directly facing gravity, if I go off like this, okay, now it's facing, well, where's it facing? It's facing off in that direction, okay? So it's exerting some force that way, which is why the keys slide off that way. Does that make sense? So to summarize, this cone, and this is the difference between, magical thing floating out in midair or it's sitting on a cone. The cone is exerting its own force, its reaction force, and it's going perpendicular to the surface of the cone, just like it was going perpendicular to the surface of the book. Okay? So I've got this tension going up this way, and then I've got the cone going off that way. Okay? Now, because it's perpendicular, rather than call it the reaction force, which is a bit generic, okay, we'll call it N for normal. Okay? So I've got N going this way. Alright, so now more colours. What force is N exerting horizontally and vertically? Let's have a look. It's got a vertical component, right? I can see it like this. Up, like that. Okay. Have a look at the horizontal component. It's not taking you toward the center. It's taking you away from the center. Why is it doing that? Why would it be pushing you away from the center? What would happen if it wasn't pushing away from the center? The thing would just go straight into the cone, right? But it's not, it's pushing back. It's like, no, you stay on your circular path out there. So these two, right, they're pushing out. Okay? So you got these two forces. Let me save you a bit of time. I'm gonna put my piece of paper underneath. Let me save you a bit of time and tell you what those forces are. You got a vertical force here of, oops, sorry, that's not Peter. That's goodbye, people who have to go. Thank you. Okay. You've got where am I? Oh, right. Okay. You got n cos 60 here and n sine 60 there. Okay, you can go ahead and you can double check the triangles. Okay? Alright. Finally, I've got a diagram and it's got all the forces on there. I used trigonometry to work out what all of these sizes were, all of the different bits, right? I've started to resolve, but I'm not finished, right? I know what they're equal to when I add everything up, okay? So let's do vertically first because it's boring. Vertically. What kind of motion is there? It's a horizontal circle, so vertically it's not going anywhere. Okay, so if I add up all of these up-down forces, they should all sum to 0, right? Okay, so I've got, let's see here. These ones are going up, these ones are going down, so they should oppose each other. So I've got t cos, I switched these around. Hold on, sorry, let me check. T cos vertically. That's right. Cos 30. That's right. And, oh no, I have some triangles wrong. I think this should be, oh no, it's okay. Yeah, no, I was right in the first place. It's okay. You can look at it from other triangles' point of view, but I think you get cos 30, it's the same thing, or cos 60. It's just looking at it from a different triangle. Anyway, where am I? I've got this. T cos 30 and n sine 60. They're going up, and then you've got gravity going down. Is that all right? Okay. So I know what both of these are. They're both root 3 on 2. Okay. So I'm going to save myself a bit of time and just divide everything through by root 3 on 2, which gives me 2g on root 3. Is that all right? Equation 1, which I got from vertical. Okay. Horizontally, what's going on? Horizontally, I have uniform circular motion. So these two forces, which are going in opposite directions, right? So there's going to be, I'm going to say a plus in this way and a minus out that way because I'm heading back toward the center. That's my default view, okay? They should add up to mr omega squared, right? So you're going to get this. Let's see here. 30. So I'm calling positive, by the way, in towards the center because that's my default mode. Okay, maybe I should put that in. Positive, okay. So t sine 30 minus n cos 60, because that's the normal force pushing out. Okay. Now, I could call it mr omega squared, but it turns out that's not such a useful way to phrase it in this situation. Why not? Because I don't know anything about angular velocity, right? I only know linear, right? So instead of mr omega squared, what was our alternative in terms of v? mv squared on r, right? Okay, so I'm going to do that instead. mv squared on r. Okay? Alright, now I know what m is. Right? It's just 1. I know what the radius is. It's a half, isn't it? A half, right? And I know what these are. They're both going to be equal to a half as well. Okay? So far, so good. So I'm going to multiply everything by 2. That'll get rid of these guys. Should put this guy up. Save you a bit of time. Here's what you get. Are you content with that? So I've divided by half here, and then I've multiplied by 2 from here. Okay, equation 2. Well done. That's that, right? That's what I got from there. I have my vertical and my horizontal forces now all resolved out, okay? Including gravity and the tension and the normal that's coming from the cone.